Okay, hi all, you all. Thank you for watching this presentation. Thank you in first place to Grey Hat people for inviting us to give this presentation about quantum computing. At first, we will talk a little about us. My name is Carlos Benitez. I'm from Argentina. I'm a cybersecurity researcher for many years, and quantum computing enthusiast. That's the reason I'm giving this presentation. And my colleague is?
I'm Luciano. I'm also from Argentina. I'm living in New York City. And I used to work a lot in InfoSec, and now I'm doing quantum computing at IBM Research.
Okay, after the presentation, of the presentation, the objective of this session is to give you some examples, some information about what is quantum computing, what you can do and what you cannot do with this, and our thoughts about the things are how things are going in quantum computing. First of all, what is quantum computing? Okay, this is a very simple definition of what we think it is. This is a kind of computational paradigm that uses quantum properties of matter to solve mathematical calculations. Okay, this is just a simple definition. But the thing we need to explain you is what's the difference between classical computing and quantum computing. In classical computing, at first, we want to tell you what we are not talking in this presentation. We will not talk about quantum mechanics. We will not talk about quantum physics. The basis of quantum computing is really quantum mechanics and is also quantum physics, but we will not talk about this. This presentation is not about quantum cryptography. This is another field. It's similar, but it's not the same, and it is not, also not about post-quantum cryptography. Okay. Okay, as I told you at first, we will not talk about physics because it's very hard to understand. Because it's completely not intuitive to understand quantum mechanics. The same Richard Feynman years ago used to say that if you think you understand quantum mechanics, it is because you don't really understand it. We don't pretend to understand it. We also are trying to explain you some of the properties of quantum particles and how to use them to do computing. That's all what we are trying to explain you. Okay. Okay. At first, we will talk a little about qubits and their properties. Qubits are the extension of bits. In classical computing, we have a bit as the elemental unit. Okay. We have a bit that can be 1 or 0. It can be resembled to a switch that can be on or off. When the switch is on, the room is lightened. When the switch is off, the room is dark. And this is all you can do with a switch, just to be in two positions, or on off. In classical computers, it's a few things that you can do with these. So what people used to do is to put a lot of bits in what we call a byte in order to represent the problems in another way, in a more extensive way, in order to use this unit to make calculations. Okay. But in quantum computing, the elemental unit is not a bit, is a qubit. A qubit has Some other properties. Qubit is rather different, rather extended, rather confusing. In a qubit, you have a room that is not exactly a room, that have different orientations, that the light might be on or off at the same time. This is a long discussion, but we can say that it can be in the same time or on off. It has a lot of states between the on and the off, the 1 and the 0, but the qubit is rather different than the bit, okay? And one of the properties that qubit has also is that you can have two qubits that they say that are entangled, that they can be very, very far apart one from the other, and the sequence of lightings and darkness inside these qubits to use this image is exactly the same in both. Nevertheless, they are very far one from the other. Okay, these are parts of the properties of the qubit that allows us to do computation in a more powerful way than with simple bits. Okay, here you can have another simple representation. A bit just can be 1 or 0. There are no other possibilities. But the qubit must have a state that can be between 1 and 0, but it can have theoretically infinite states between both. Okay, the qubit is usually represented as this block sphere. This is a vector. This is represented as a vector that is centered in the center of the sphere, and the length of the vector is 1, and the state of the qubit can be anyone in the surface of this sphere. There you have two states, 0 at the top and 1 at the bottom. But the qubit can have a lot of states between them. Okay. These the qubit has three main properties that we are using to make this calculation. One of them is the superposition. Superposition means that the qubit can be, as I told you, there is a long discussion about that, but we can say that the qubit can have the two states at the same time. This is the famous Schrödinger's cat that can be, until you open the bag, it can be alive and dead at the same time. Okay, we will not enter in this discussion, but the concept is that you can have both states in a superposition. Okay. The other property of the qubit is the entanglement. As I told you, when I showed you the two rooms very, very far one from the other, when you entangle two qubits, the two are not independent. The two are connected, and both qubits can act randomly, but this randomness is exactly the same in both of them. Okay, they are connected. If you read one of the qubit, the state of one of the qubits, the other qubit has exactly the same state at the same time. Okay, and the third property is a property that is not good. It's a property that we want to get rid of it, but we cannot very easily, which is the coherence. The coherence means that it's a kind of noise. When you put a qubit in a state, the qubit, the state of this qubit tend to go back to the original state, normally ground state or 0, and the state that you set to this qubit stay for a very, very short time, rather some microseconds. So you have to use this information, this qubit, in between this window of some microseconds, in order to be useful. Okay. Okay. With this property, we can do some calculations. Which are the calculations that we can do with qubits? Okay, mainly rotations. These are 6 examples of 6 rotations that you can do with a qubit. As I told you, the qubit is represented as a vector with center in the center of the with origin in the center of the sphere and the end in the surface of the sphere. So putting this vector in different positions inside the sphere means rotations, and that means that are the calculation that you can do with a qubit. Okay. The different operations or calculation that you can do with a single qubit are done in quantum computers with gates, mainly with gates. And this, I want Luciano to assist me in this. He is an expert in quantum computing at IBM, and he uses these gates every day. So please, Luciano, tell us about these gates, please.
Gates, quantum gates are analogous to classical gates, like, for example, XOR, AND, or NOT. And as classical gates, they may have multiple inputs. For example, in classical gates, the NOT gate has 1 bit input and 1 bit output. So similar here, you can have some gates that are operating 2 qubits or 1 qubit or 3 or more qubits. The most important one probably is H, the Hadamard gate, is the one that you show in the previous slide. It's a half rotation that puts the qubit in superposition if it starts in the ground state. If you apply a Hadamard gate to a superposition state, you will get back to the ground state, for example. So we said that gate is self-inverse. If you apply it twice, it's like applying none. Some other gates are not self-inverse. For example, the S gate is a rotation that you need to apply S dagger in order to go back to the same place. So the inverse of S is S dagger. Same applies to Chi. The one with the circle with the cross in the middle is not. It's basically also a single qubit. Sometimes it's called an X gate, and basically negates. It's a 180 degrees that negates a 0 into a 1, or but basically makes that rotation. So whatever is your initial position, you will have that position on the other direction. And there are other multiple rotations. There are arbitrary rotations that you can do on the different axes, X, Y, Z. The full surface of the sphere is fair game. So you can point wherever in that quantum sphere. There are some of these that you have here at the screen. They are not gates per se. We call them instructions. They don't have this characteristic of being reversible. For example, those in gray are instructions. So, for example, it's possible to do a reset of a gate, which is basically the second one which has a 0 inside. That one is a reset instruction. Basically, in whatever state was that qubit, put it back into the ground state, into the 0 state. And another important instruction is measurement, which is the last one of the gray ones, which is basically whatever is the state of this qubit, collapse it into a 0, 1 in order to measure that. And the probabilities of measure 0 or 1 will depend on the position where that qubit was, the state in that qubit. Do you think that will make it, Charlie?
Yes, of course. Thank you very much. I wanted the expert to explain this. Okay, so when you have, let's say, 1 qubit, you can do much more things than just putting on or off like a bit. And so how we solve problems with this, okay? Okay, the way of solving problems can be explained here. A vector rotation inside a sphere can be represented as a matrix multiplication, okay? When you rotate this vector, you can put the positions of this vector into a matrix then multiply, and the results will be the vector rotated. So the main idea here is that you can use the qubit as a matrix multiplication. So if you have a problem that can be modeled as a matrix multiplication, you can go back and solve it into a qubit or into a quantum computer with a set of qubits. Okay, it's not too much what you can do with just one qubit. Okay, so to do this, let's say you have a problem and you want to solve this problem inside the quantum computer, because as you know, if you have to solve a matrix multiplication in a classical computer, it will take a lot of time, a lot of calculation, a lot of iterations to do that. And you can do this just with a single shot in a quantum computer. This is the power of this kind of computers. Okay, so let's say.
Let me mention that additionally, there is a thing with the space, the size of the space. I'm not sure if you're going to mention.
Okay, of course.
Shall I show it?
Please.
So check out this example. This is Hadamard gate that operates on a single qubit, and the matrix that it represents is a 2 by 2. If you have a 2-qubit system, you can represent a 2 to the power of 2 square matrix. So as you add more qubits, you double the space in terms of the size of the matrix that you can represent. So in a 6-qubit system, you will have 2 to the power 6 by 2 to the power 6 matrix, and quickly that classically gets unfeasible, right? To operate with big matrices, it's something that classically is very hard to do, and quantum computers are particularly good at doing.
Yes, of course. These are the two main powers or superpowers of qubits. The representation space that scales very, very fast compared with bits, with classical computing and bits, and the power of the speed of computation, because you can solve these huge matrices just with one shot. So this is the reason why so many companies and so many labs in all the world are trying to achieve their best effort to do their best quantum computers, because the power is really huge. So let's say you have a problem and you want to solve it. You have to solve mainly 4 challenges, okay, with this algorithm. Oh, sorry. This is what the problem you would have to solve. Okay, 2 + 1 = 3. Where in a classic computer, you normally convert the decimal numbers to binary numbers, and you do this there, and you get the results here. This is one of the ways that you can solve this. Okay, in computing, you can do the same. The difference between quantum computer and classical computer is that you don't have exactly like a binary gate, but you have a quantum circuit. The result will be made by quantum gates and some instructions like this reading instruction here. Okay, this is what you get when you finally build a quantum algorithm there. Okay, so as I told you, you have to solve mainly 4 challenges. The first challenge is the model. You have to model your problem as a matrix multiplication. If you cannot model the problem as a matrix multiplication, it would be very difficult to be solved in a quantum computer better than in a classical computer. Okay, you can solve it because a quantum computer is Turing complete, but you cannot do it faster than in a classical computer. This is the first challenge. The second challenge is that your quantum circuit, as I showed you recently, has to fit in your hardware. In current quantum computer hardware are rather small, with several at most hundreds or qubits are very, very, very small in their size. So you have to be sure that your problem can fit the quantum circuit that was the result of your problem can fit in the computer. The other one is have to run the problem many times in a quantum computer, because as I told you, by the coherence or by noise, you can have several times wrong results. So you have to run it many times in order to statistically say, okay, if this result have been the output of my computer 80% of the time, and this result 20% of the time, okay, I take the 80% as the correct result. Okay, this is a strategy that you have to define. Okay.
Let me make a footnote there.
Okay.
It could be possible that your problem has more than one solution. And
okay. Also,
in a single execution will only give you one of those solutions. So even if you run without noise, sometimes you can try it several times, so you can see that statistically, those solutions, for example, they have 50% of chances, or maybe a solution has more probability than the other one, but you want to, the result is this statistical description of the possible solutions, even when some of them, they may be the wrong solution because of noise, as you said.
Okay, great, thanks. That's true. And okay, and the fourth challenge is noise. You have noise in many sources. One of the sources, as I told you, is the coherence. You have this solution will be present in a qubit just for a very, very few microseconds. You have to do something with that to feed another qubit, or to read the solution before it falls to the ground state. And you have another noise sources, like, for example, thermal noise. You have thermal noise. That's we will talk about this in a few minutes. Okay, let's say we have a problem. We have made an algorithm that with that algorithm we have the result is a quantum circuit. With that quantum circuit, you have to solve these 4 challenges, and we will run this to solve the problem. Where we will run this? In some kind of hardware quite different from the hardware you are used to. This is the hardware you already know, but quantum computers are quite different. Here we have some examples. This is with Sycamore, for example. This is one of the machines from Rigetti. That is a company that does only their purpose is to work in computing, in quantum computing. This is, for example, a quantum computer from Microsoft. Microsoft is working in a completely different technology than the others. And for example, the IBM Q53, this is one of the IBM's quantum computer. All these pictures you are seeing are not exactly the same that you can see in the labs. They were touched by the artist, but are more or less like this. If you see, if you look at the bottom of this computer, you have a cylinder there. If you take off this cylinder, you can see inside this small black square, this is the chip. This is the quantum chip. Okay, the quantum computer is very different from classical computer, but the chip, no, the chips are very similar as you can see. This, for example, is a very recent achievement from IBM. It's a quantum chip of 65 qubits a couple of weeks ago. And how these chips are works. For example, here you have a proof of concept from 10 years ago from IBM 2. This is a proof of concept just from 1 qubit, okay? And this a processor, a quantum processor from 5 qubits. If you see in the center of the image, you see 4 squares. Sorry, 5 squares. These 5 squares are the 5 qubits in the chip. As I told you, there are several technologies to do a qubit. A qubit is a physical representation of a quantum state. As you know, say you can see a quantum state in a quantum particle, okay? But you cannot work for your computation with a quantum particle. You cannot take a single photon or a single electron and change its state. You have to do this with a lot of different techniques that can behave like a quantum particle, okay? There are several techniques. One of them, the most used, is the superconducting technology. A superconductor is a material, is a very strange material. You have a couple of hundreds of material that became superconducting. Superconducting means that you can have a material that the resistance is completely zero, okay? But this occurs just below some critical temperature. And this critical temperature is really, really low. One of the materials that is most common use is aluminum, and the aluminum is superconductor below 2 or 3 Kelvin degrees. As you know, 0 Kelvin degrees is the absolute zero. You cannot go, physically it's impossible to go below 0 Kelvin. Okay, quantum computer chips works about 15 millikelvins. So that's the reason the strange shape that you can see in those photos recently, because all that hardware that you see, 99% of the hardware is just to keep the quantum chip cool. This is the only reason, to be below 1 degree Kelvin. A footnote for this is very crazy, because if you see in the outer space, in place very far from any object, you can measure 2 or 3 Kelvin degrees, and if these chips are at 15 millikelvins, that means that you have in these computers temperatures below the temperature even in the outer space. Okay. How quantum computer looks like. This is more realistic. As you can see, this container is just to keep this really cool inside. This is a picture about how different companies are working and running to achieve their quantum computers. Some of them, and all of them in different directions, really. Okay. We have recently discovered a new technique, a new company named Xanadu, that they claim that they have a quantum chip that works at room temperature. This is really cool because, as I told you, it's very, very difficult to achieve so low temperatures. They use photons as qubits, This is a really new achievement. And you also have, besides all the companies I show you and the quantum computers I show you, you have them also some people really in the East working on this. Here you have Chinese people working in a channel microscope that is very important to build quantum chips. Okay, great. Before going to the demonstration, we want to tell you about some myths and facts about quantum computing. We will tell what it is said over there about quantum computing and what is the truth about all of them. One of them, what they are saying is that quantum computers can run the same programs than classical ones more efficiently. Okay? Okay. No, quantum computers can run only certain algorithms more efficiently. As I told you some slides before, if you can model your problem as a matrix multiplication, maybe you can run this problem in a quantum computer really, really faster than in a classical computer. But if you want to do other things that are not modeled like matrix multiplication, it would be very hard to do that really in a quantum computer. Okay. Other myths that are over there, you can see all this in internet, is that quantum computers are going to outperform classical ones. It's rather similar to the other saying. Yes, but only in some specific tasks. Okay, there will be another task that will not be really do well by quantum computers. Other myth is that quantum computing means the end of classical computing. Okay, really, what maybe will be the future is that classical and quantum computer will work together in a kind of hybrid architecture, in the way that any of them will solve problems of their fields efficiently, really efficiently, but none of them will replace the other. Okay. One of the really well established myth is that quantum computer will destroy cybersecurity. They are saying this because of some algorithms that can solve large number factorization, like short algorithm. Luciano will show us this. But no, really no, because quantum computers are just part of security. Cybersecurity is formed by many other concepts, like, for example, have your servers properly configured, have your application properly built. There are a lot of other things that are not cryptography. And in one side, and in the other side, you need about 100,000 qubits to break a key to 2,000 key bits key in seconds. Okay, so not really. And the other thing that people are saying about not only quantum computing but quantum mechanics itself is something like this, that quantum computers that are very related to machine learning. Machine learning is one of the problems that people want to solve with quantum computer, and they are very good doing this. Okay, if you can put machine learning in a quantum computer, and the quantum computer is enough big, this computer will become conscious. Okay. And this is what we think about that. It's really a very long distance between a very good machine learning computer and that machine can become conscious. Okay. I'm finished by now, and go to some demos that Luciano will bring us.
Here, let me share the screen.
Okay.
Is it?
Perfect.
Awesome. So let's start with it with some hands-on on the framework that I'm most familiar with, that is Qiskit. There are many frameworks out there for playing with quantum computing, but this one is rather popular. And before that, let's talk a bit more about this notion of a quantum gate and this analogy to classical gates, right? Here in the top of the screen, you have a classical XOR that takes 2 bits as input and computes the exclusive OR and gives you 1 bit output. Similar to this gate, you can have also quantum gates, as Charles explained. And a very common one is this one called CNOT, which is usually used for entanglement. And in a rough sense, and just like for familiarity, it works a bit like a conditional, like an if. So if the wire on top, the X wire, is 1, it will apply a CNOT gate to the bottom wire, to the wire Y. And in this way, you can compute similarly like the XOR operation that we have classically. The interesting situation is what happens when X is not in a classical state 0, 1, but in superposition states. But for now, we can simplify it like that, right? And also notice that we talk about that the quantum gates are reversible. That means that with the output, you can reconstruct the input. And that's not something that happens per se in classical gates, right? So for example, in the XOR from the top, you see that that with the output, you cannot reconstruct the input. So in order to add that property to a classical gate, we had to add this extra wire that you can see in the right-hand side. So with this information, with this introduction, let's jump into the game. So the first thing that we had to do is to import some Qiskit utilities, and then let's jump a bit with some of the properties that gate has. Let's take, for example, the Hadamard gate. This Hadamard gate is the one that is superposition, right? And as Charlie said, they can be represented as qubits, as matrices, right? This matrix is what is called normalized. Doesn't really matter what that means, but something that I would like to focus on is the fact that the size is 2 by 2 because it's a 1 qubit gate, right? If we do the same with other gates, for example, the CNOT gate, the CX8 or the CNOT gate is the one that we have here on the top. That operates in 2 qubits and therefore is 4 by 4. And you can also do a CCX, like it's basically like this one, but with 2 control wires, so operates in 3 qubits, and therefore the matrix that represent is 8 by 8. So you can see here what I mean before with this representation space that you can get with qubits. Another important thing to mention is that these matrices, they operate in the complex space, right? It's not in the they are not natural numbers, so they are not integers. They are complex numbers. So let's start first with a classical circuit. Let's call it Bell state, and it's a very common first step. It's called the hello world of the quantum computing, right? And you can when we know that H and C0 are 2 matrices, so we can compute the multiplication of those 2 matrices, and we're going to have this as a result. Again, it's a 4 by 4 because it's a 2 qubit system. And another thing that we can do is to measure it, right? So let's have the same circuit, and now if we can measure what's going on there, half of the time, so we can run this 1,000 times to have a statistical results, right? And half of the times the result was 0, 0, and half of the time the result was 1, 1. And why is that? Well, because this is a position, this gives you 50% chances of being in one position or the other one. And then the CNOT gates applies the NOT gate. Most of the time, CNOT are both than NOT. So therefore, you can see the dependency between those 2 qubits in what is called entanglement. So let's now go into our first algorithm, because all these things are, it's hard to see how these kind of things can be useful, right? So let's jump onto something called the Dodge algorithm, which main focus is to show where is the advantage of quantum computations over classical computations. It's a bit of a made-up problem, so bear with me. The only purpose is to illustrate the point of quantum computing being more powerful. So take a function that has one. Sorry, take a function that has as input 1 bit and as output 1 bit. There are only 4 kind of functions that have that property, that takes 1 bit and return 1 bit. Half of them we are going to call them balanced, and half of them we are going to call them constant. If the output is independent of the input, in that case we're going to call it constant, and if the output is dependent of the input, in that case we're going to call it balanced. There are only 4 of these functions by construction, so we know that that's good, and also we are only two categories, balanced or constant. There are no third option. So let's now put one of these functions inside a box. That box we're going to call it an oracle. So we can ask questions to the oracle, and we can see the answer from our oracle, but we cannot. We don't know how is the oracle built. So the problem that Deutsch tries to solve is the following: if I don't know which is in the function in the oracle, how do I know if the function in the oracle is balanced or constant? So classically, in order to answer that question, I need to run the execution twice. I have to ask 2 questions to the oracle. I have to say, okay, give me the answer for the input 0, give me the answer for the input 1. If both answers are the same, therefore the result is constant.
Exactly.
If they are not, in that case is balanced. So that's the classical answer to Dodge algorithm. The quantum answer to Dodge algorithm can be done only with 1 question, with 1 execution. And for that, we need to build this quantum oracle. And we know that gates are reversible. That's why we had to add extra wires here in the quantum version of the oracle. But basically you stay with me that the oracle classically in quantums is the same, but the things that we're going to put around it are the part that differs. So in order to see how this works, let's start by first construct these 4 functions into a quantum machine. As Charlie also mentioned, these functions are classical functions, but we can represent classical functions in a quantum computer too, right? So the first one that we're going to represent is the constant 0. It's the simplest one, right? Doesn't matter the input, the output is always 0. So basically it's the empty circuit. The initial state of qubits is the ground state, 0, and I will not change that ground state independently of the input. Then the constant 1. I will ignore the input, and I will always have 1 as the output. Because it's constant, I can apply a NOT gate, and that will turn the 0 into 1 in the output wire. The identity one is a bit more complicated, but we already know how to solve it, right? Because we already know how CNOT work. If the output is 1, in that case, I will apply a NOT gate in the output. If the input is 1, in that case, I will apply a NOT gate in the output. And if the input is 0, in that case, that NOT gate will not exist in the output, and therefore the output will be 0. It's the identity. Input 1, output 1, input 0, output 0. And the last one is invert. It's basically like identity, but at the end, I do the inverse. I flip the output. So let's now make a test to see if those things work as they're supposed to work. So let's create one circuit. The things between the bars, we call them barriers. Those things are the function itself. And the thing in the X that I put out is the input, right? So for example, the input that I choose here is 1. The input is 1, and now I'm applying the invert function here. And if I execute this, if I execute this several times, it's always the same result, right? Because there is no, and the deterministic, this is a classical computation in a quantum circuit, but it's a classical computation. Therefore, it's deterministic, and therefore, I always get the same result, 0. Because the input is 1, I apply the inverse, and then the output is 0. So if I instead of doing invert, I do identity, the circuit is slightly different, and always the output is 1. If the input is 1, the output is always 1. Okay. So now with a bit more confidence that our functions work as they're supposed to work, let's go into the Deutsch algorithm itself. So consider this situation. Now I have this function inside the box that I call oracle. I have the oracle of 4 that I already forgot which oracle is that one. And the things that we put around it is the algorithm itself. These Hadamard gates, these things around it is the algorithm itself. We're not going to change the difference here, what they do, but if you're invited to do the math and to see how this works. But for reasons of time, we're just going to run it just to try to make the bond here. So let's see if the result is 1, that means that the output is balanced. If the result is 0, that means that that the function is constant. Yes. This is the way that it works. I make this small translation so you don't have to remember that difference. And for example, the oracle 4 says here that it's balanced. Deutsch tells us that the oracle 4 that is running here is balanced. Right, and I only did it in only one execution, in one shot. If I do it several times, I will get always the same result. But the important part here is that you can do it in one execution, right? So that's why, as promised, I will only use one shot. And let's see if the oracle 4 is indeed balanced. Here the function invert, it is balanced indeed. We can try to add the oracle for the sake of trying. Let's check it out the oracle 2. And the oracle 2 tells me that it's constant. So let's check it out. If the oracle 2 is the constant 1 function, it's always 1, independently of the input. So the Deutsch is getting always the right answer, right? So hopefully this is an invitation, if not convincing, at least an invitation so you can go deeper into what's going on here. But tries to illustrate that only with one execution it is possible to answer questions that classically it require 2 executions. Let's now jump on the bad side of quantum computing, to call it somehow, and that happens when we deal with real devices, right? So far up to this point, we have been running everything in a simulator that simulates a quantum computer, an ideal quantum computer, but real quantum computers are hard to deal with, right? And the reason for that is because, as Charlie also mentioned, the problem of noise. So let's try the same Deutsch algorithm, but in a real device, right? So for that, I will ask to the IBM cloud service to give me the less busy backend that is not a simulator and has at least 2 qubits. And the backend that is bringing back, it's one called IBM Q Valencia. This is a backend with 5 qubits that they are organized in a particular way. That means that, for example, it's possible to do a CNOT between 0 and 1, but it's not possible to do a CNOT between 0 and 2. That kind of limitations is the one that Charlie refers to. I have to make sure that the problem fits in my hardware. That's one of the challenges that we have to solve. And there are 13 pending jobs to be executed on this hardware. So even when it's the least busy one, it's quite busy. And the important part that I would like to show you here is this part, the part where I have information about the error. So also, as Charlie mentioned, there are a lot of sources of error. There are errors for the coherence, basically just for time passing, that it's hard to hold the quantum state. There's errors in the calibration when we try to set a signal in a particular state. It's imprecise. There are errors when we read that particular state. There are errors all around, and it's the kind of things that add noise. And now let's send our secret instead of to a simulator to this quantum computer. This process will take some time because remember there are some jobs in the queue. So we can come back in a sec when the result is there. Let me see if I check it out, how long this may take. So the job that I just sent, I can check it out. What is the status of the job? Is still waiting in the queue. And at some point, this status will be done, and we can see what are the results for that. So let's wait for some time for that.
A few moments later.
Okay, now we are back. Now the job is done. And let's see what are the results of that job. So let's check it out. The result was that many times the result was constant. And let's see, check it out that indeed the real result is constant. In the ideal simulator, the result was constant. That makes sense. But notice there are some times that the result was not constant, right? Let's see how many times. So 6 times the result was not constant, right? And this is the consequence of the noise, of the fact that we are running in a non-ideal computer, in a real hardware. Now let's go to the part that probably you are waiting for. Is let's try to factor a number. And yeah, we're going to factor a small number, 15. I hope you're not disappointed with this situation, but because it's really not. In the current state of quantum computing, there is not really much more than we can do than try to factor 15 number. As a matter of fact, it's even hard to factor 15 in a real computer. So usually we do simulations for factoring something like 15, and that's a hard problem. And the point of this demo is so you can get a bit of an understanding of why this myth that the quantum computer is the end cryptography
classical computer, yeah.
of security in general, of classical in general. And it's because things are not so directly, right? So we're going to jump on is something very famous called the short algorithm, which is a way to factor numbers. So there are very many cryptographic systems that the strength of that system is based on the fact that you cannot easily factor a very large number. The same thing applies to discrete logarithms and the kind of things. So it is possible to run the short algorithm in a classical computer. It just basically takes as much as factoring a number, right? It's super polynomial. So the point here is that we're going to split the problem in two. We're going to turn the problem into finding an order. And this kind of order finding problem is something that it can be represent as much as multiplication, and therefore quantum computers are better at than classical computers, right? But also this is a problem that can be solved classically, happens to be super polynomial, but a quantum computer is not super polynomial, right? And the way that the strategy that this has is that basically we are going to have several tries, and we're going to get better guessed in every iteration, right? And here we're not going to jump into the details of what that requires, but I would like to give you a hint on the size of the kind of qubit. Right? So the first thing is requires 2 attempts, because I told you factoring with short algorithm means making guesses and making better guesses in each iteration. In this case, for example, it requires 2 attempts to factor 15. And indeed, it found the factors, 5 and 3. And let's figure out what is the kind of circuit that we need for doing that. So this is the circuit that we need for running short algorithm. And each of these boxes, it's particularly big. I mean, even when it doesn't sound big, the hardware cannot implement these boxes per se. So we have to decompose this in small gates that can be implemented in the hardware. And at the end, there is something called the QFT. That's the quantum Fourier transform. but also is something that has to be decomposed in several gates. In how many gates? Let's check it out. The first thing that we have to do is to choose a backend. In this case, we have to choose something that fits our problem. Here we need 12 qubits, so we need to choose something big enough. The best thing that we can fit in is in the IBM Q16 Melbourne. This computer has 15 qubits, and notice that the amount of gates that can implement are not the same amount of gates that we need, right? So these gates, they need to be decomposed. They need to be getting into primitive gates that can be implemented. And let's see what happens if we want to execute that circuit that we have in the top into this backend. For that, we have to do something that we call it transpile, which is similar to the compilation system, where we adapt a quantum circuit to a specific hardware. So this will give us a circuit that fits into the hardware where we want to run the circuit in. It takes some time. It's understandable because it's a very, so the compilation process is the one taking some time here. We are not executing the circuit itself, but we are adapting the circuit to the hardware specifically. And now we can see what kind of operations do we have there. For example, it requires almost 19,000 CNOTs, requires around 12,000 single qubit operations. It's a relatively big circuit, only again to factor 15, and a circuit with this depth. Basically, the depth is so we can even measure the depth here. Let me see. Physical circuit depth. I think yes. The circuit with this depth, the amount of gates that we need to apply in a circuit is 19,000. That means that the coherence will not hold that long, and therefore the result will be just noise, right? So also, it's important to note that just trying to factor 15 is already a challenge, a big challenge for nowadays real quantum computers. But the hope is that the technology gets better, and we're aiming to that, right? A small army of scientists trying to find the answer to a lot of open questions to improve the hardware. The goal of IBM for 2023 is to have a computer that can execute 1,000 qubits. Still, that will not be enough, but with time, we're going to get better at this. Charlie?
Okay, but we are very far from absolutely breaking the security with quantum computers, as we can see, we saw today. Okay, just wrapping this up, some conclusions about this. One thing that we didn't mention was something about quantum supremacy. There are a lot of companies that are trying to achieve quantum supremacy. It is important because this means that it's different achievements in this race. But quantum supremacy itself doesn't mean anything if you want to go to practical results of this. Okay, in fact, we have. Many of you maybe remember news about Google achieving quantum supremacy last year because they could solve a problem a problem that is not practical, but it doesn't matter. Quantum supremacy said that you can solve problems that are not relevant, but that cannot be resolved in a practical way in classical computers. Okay. He claimed that they did that, but IBM a couple of weeks later said that it was not so, because they could solve the same problems in a supercomputer in a couple of days. So they didn't achieve the quantum supremacy. Okay, this is one of
the claim from Google was that they created a problem. Again,
yeah,
useful or practical problem in any way, but quantum supremacy is this idea that it's possible to solve a problem in a quantum computer in a time that is feasible, while solving the same problem in a classical computer is not feasible. So Google create their own problem, and they solve a problem that, according with Google, require 10,000 execution years. And IBM showed that it was possible to solve that very same problem in some days. And again, this quantum supremacy is talking about a problem, and this problem is not useful in any way.
No, of course. It's just to do some progress in the quantum computing race. Okay, so what we think, we are in an age of quantum computer like in 2008 years, when they started to use vacuum tubes to do something in electronics. We are very, very far from doing things that will really, really change the world that we know. Okay. Okay.
The analogy is very close to, because also quantum computers, as primitive classical computers, they still also require a group of people going around them, constantly keeping the electronics running, recalibrating. So they really require people on the ground, on the lab, to keep them running, as was true for the first computers, classical computers that we have several decades ago.
Okay, so what is real is that there are a lot of quantum computers. There are a lot of companies that are working a lot to make this dream possible. And here you have 6 of them that are publicly available. Some of them are more available than the others, but never mind. You can apply to these sites, to Xanadu, to IBM, to D-Wave, to Rigetti, to Microsoft, or to Amazon, to learn to use these computers, to play with them, and to make this wheel move faster. We encourage you to do that. It's very interesting. This really cutting through, and we hope you can go and do your own algorithms that are really useful for someone or for humanity. Okay. So here you have some references about what this presentation we have used, and we want to thank you a lot for being there. And these are our contacts. And thank you very much for being watching this presentation.
Thank you, and see you in the next Grey Hat, hopefully in a physical place with physical people. Bye-bye.
We hope so. Yeah. Bye-bye.